Welcome back friends. So, we are in now going through part 2 of this course on fundamentals of materials processes. In part 1, as you remember, we went through solidification, fundamentals of solidifications, and the other module was fundamentals of powder metallurgy. In this part 2, we will be again covering two different aspects of materials processing, fundamentals of metalworking, which I will be taking 10-hour lecture on that, and then there will be 10-hour lecture on fundamentals of thin film deposition, which will be taken by Professor Anshu Gaur. So, I hope most of you have gone through the first two courses, but if not, it is not a issue, because both of these are independent courses. You may go through those lectures, the NPTEL lectures, they will be available online. You can go through them and understand the fundamentals of other two aspects. As of now, we will go through these fundamentals of metalworking and fundamentals of thin film. So, when we are talking about metalworking, what are the things that we will study? Let us jot down a small list of items that we will go through. So, here we will be going through fundamentals of metalworking. What are those fundamentals? The most fundamental is, of course, understanding about stress, strain, and the yield criteria, because whenever you are doing any kind of deformation, which is the large fraction of processes that come under metalworking, there you need to understand what is the yield criteria, because we cannot simply define those in our original simple terms of tensile test and the yield plasticity from the simple unilateral tensile tests. And therefore, when we take a look at stress strain, we will extend it further to understand yield criteria. Then we will move on to understand flow behavior, again related to stress strain and related to yield criteria. Then we will take a look at understanding effect of strain rate. You will realize very soon through the course that there are three very important parameters when we are talking about metalworking: strain, strain rate, and deformation. These are the input parameters that you impose during the formation or the deformation processes, and therefore effect of individual, the combined effect, all of these are important to understand. So, once we have the effect of strain rate, we will also understand the combined effect of strain and strain rate. Then we will understand the effect of temperature and the combined effect of all three. And then we will take a look at go through some of the simple models to understand the mechanics, and through that we will go through some of these processes like rolling, wire drawing, extrusion. These will be our main topics or the main examples that we will use in understanding the mechanics, the force requirement, and so on. Now, when we say metalworking, what are the examples that come to your mind? One of the most common process, not most, but some process that you must have heard of is something like this. Can you guess what this is? Here you have two anvils which come together, and you have a workpiece in between these two, let us say a rectangular block like this, and this is usually at high temperature, and these anvils are forced against each other. So, this is extrusion. Now, in extrusion you would want to know what is the strength or load at which this material will start to deform. What is the force because according to that you will determine what will be the force that you will supply to these anvils. Then once you know, then you will also need to know at what rate these anvils should move, because what will that rate determine? That rate will determine the strain rate. What is the strain rate? Because different material will have different properties at different strain rates. Now, it is not only the strain that makes a difference, it is also the strain rate that makes a difference. Then why are we using high temperature? Why not at room temperature? Of course, one of the simplest explanation is that at higher temperature you are able to deform the material easily, but at how much high temperature? Would you like to have it very close to the melting temperature? That will require you to heat it to a very high temperature, which is very energy consuming. So, all those questions need to be answered, and that will be answered only if we are able to understand the relation between stress, strain, the effect of temperature, and the interrelation between these on the material. So, this is one example. Another example where you would need to understand the fundamentals of materials processes for metalworking is the most common that you might have heard of in all the metalworking process, and that is rolling. So, you have two rolls, like mostly two rolls, you can even have more than two rolls, and you have a slab that is going in like this and a slab coming out like this, and these are two drums which rotate like this. Now, once you look at it, it will look like a very simple process, but there are several intricacies over here. First, what is the strain? Is the strain just in this direction, or is there strain also in the longitudinal direction? And not only that, in most of these cases we assume that the strain in this third direction is 0, which means that it turns out to be a plane strain condition. And in the plane strain condition, how are the different elements getting deformed? What is the strength? What is the what should be the load that should be applied by these drums onto the material? Can it be thinned down to any extent? All these answers will come only if we understand the fundamentals. Not only that, look at the velocity of the material of this sheet that is passing. Now, if this is being deformed and it is thinner out here, then obviously the velocity at this part is much larger than the velocity at this part. If we assume that this part is twice the thickness of this, it means that the velocity here is twice that of this region, which means that at this point the material is moving at, let us say, V1, then at this point it is moving at V2. So, there is a continuous change in velocity from here to here, but the drum is moving at one single constant velocity, and therefore, it would mean that the drum is slipping against the material at each and every point except at one point in somewhere in between, where it is exactly the velocity of the drum is exactly equal to the velocity of the slab over there. What does that lead to? That will lead to a lot of friction. How does that friction play a role? Is it good? Is it bad? All those things we will be able to answer when we get through the fundamentals of this course. Let us look at still another example, which is extrusion. Now, their extrusion can be direct extrusion, it can be indirect extrusion. The one that I will draw over here is direct extrusion. So, you have a die like this, and inside you have a piston which moves like this, and in here you have metal which is forced through this orifice, and you get longitudinal structure. Now, this longitudinal structure can be of any cross section. For example, it can be a L section. You remember having seen those L frames, the aluminum shaped L frames. This is how they are manufactured. They are extruded. Now, here this is direct extrusion, meaning the piston is moving in the same direction in which this part is getting extruded. However, we can have different shape or different configuration, where when you press in this direction, actually the material will also come out in this opposite direction. So, that is called indirect extrusion, and there are advantages and disadvantages of both of them, and there are friction, one of the most important one is the friction considerations. But not only that, how much again the strain is required, what is the yield, what is the strength at which or the stress at which the material will deform, it will start to yield or flow. So, those things we will be able to again understand only if we are able to go through this course. Now, these are some of the deformation processes, but there is still one more process that you may not usually associate with metal working, but it is also metal working, and that is machining. So, here I am drawing one particular example of machining, which is plane strain machining by the lathe machining. Here this is your cutting tool. So, this is called a single point machining. This is your workpiece. There are several different kinds of machining process which all come under metal working, and this is your chip that is forming out. So, this is you are removing this part is getting removed, and this is also metal working. Again, not only how much load that will come onto the cutting tool, which will determine what is its life, but also the strain rate and temperature will be different depending on what is the machining configuration, and because of that there will be different microstructure on the surface leading to different properties, and for that we need to be able to predict what will be the strain rate and temperature. So, one thing that we are able to gather from until this point is that there are three important parameters when we are talking about metal working in most of these, and that is strain rate and temperature, particularly during deformation, and that is what determines the not only how much load is required, but also what will be the final properties of the material. So, that is what our whole course or these next 10 lectures will be rotating around. Now, before we move ahead, it is important that we have or describe some classification for metal working. So, the metal working can be described into two main groups. One is metal forming, and the other is metal cutting or metal removal. So, all the machining processes like drilling, grinding, machining, all these come under metal cutting. So, you are involved with removal of material. In here you are always involved with some kind of deformation or giving a shape to the metal. So, deformation or giving shape. So, these are the two broad classification, but even under these we can further subdivide them into some more based on what is the direction of the force. So, one of them is direct compression, indirect compression, so this is basically describing which direction the load is working or the force is working onto the material, because you are doing deformation or giving shape. So, you are applying some load or force onto it. Now, which direction is it? Is it compression in the direct compression mode like in the extrusion that we saw, or is it indirect? So, like in the indirect extrusion, that was the indirect compression. Tension, when you are pulling something like a tensile test that we conduct, or when you are pulling a rod, for example, in wire drawing. Then we have bending, for example, sheet metal working that involves a lot of giving edges to the metal, that involves bending, and then shearing, like cutting the metal, cutting in the sense metal sheet, cutting the metal sheets when you are dividing it or taking off a portion of it, then you are shearing it. And this is most of the metal cutting processes, like we said, where you are, the main purpose is to remove the material. For example, you may be trying to make some chamfer, and over there you will cut or remove the material. So, you will be doing some kind of cutting. So, all those processes come under this. So, this is based on direction of load. Now, when we are doing deformation, you will see that there are three main temperature zones people use, and that has to do with the physical metallurgy of the materials, because in these three different zones materials behave completely different, and therefore, these classification of metal forming can again be divided into three different zones or temperature zones: cold, warm, hot. And when I say cold, warm and hot, it is not at the absolute temperature. For example, even if you cold or even if you roll lead at room temperature, it is not cold rolling, it is actually hot rolling, because it depends on the temperature at which the material melts. So, with respect to that, we describe a temperature and divide it into three zones, which are called cold, warm and hot temperature zones. So, this is one classification of metal forming, and overall we have metal working in two different classifications: metal forming and metal cutting. There is still one more classification for metal forming, and which is based on what is the thickness of the material. So, for example, if we are dealing with bulk material like very large pieces where we are, the main purpose is to give a shape, then it is called bulk deformation. And the other one is when the purpose is not to make or give any shape, but just to change the configuration, like in sheet metal. So, these are called sheet metal working. And some of the examples we have already seen, for example, extrusion, rolling, etc. All those things that generally we relate with deformation are actually nothing but bulk deformation. On the other hand, sheet metal working involves something like bending operation. So, if you have a sheet metal and you want to give it a L shape for whatever reason, or you want to have a emboss on the metal sheet, then those kind of operation you are not actually changing the shape, you are just changing the configuration. So, the main purpose here is changing configuration, and something like bending, shearing, embossing, these are all related to sheet metal working. So, if we were to define it, then bulk deformation would be characterized by of course bulk deformation, which means bulk plastic deformation, which implies massive shape changes. And when we say bulk, what we mean is large, or actually low surface to area volume ratio, low surface to volume ratio, meaning for per unit volume the surface has to be low. On the other hand, if you look at sheet metal, per unit volume surface would be very high, because these are sheet, these are flattened out surfaces. Here usually compressive stresses is what is used. Usually compressive stresses are what are used. Now on the other hand, when we talk about sheet metal working, this is characterized by local deformation. So if you look at a bending operation, what you would see, sheet metal like this, it has been bent from a flat shape into this. So where is the deformation taking place? It is taking place only in this region. So it is a very localized deformation that we are talking about, and therefore it is characterized by local deformation. On the other hand, if you remember when we were talking about extrusion or rolling or forging, on all of those, whole of the material was actually getting deformed. So the deformation was not limited to any local region. And here stresses can be mostly shearing, but it can as well be tensile, compressive, etc. So these are some of the classification that is very commonly given in textbooks that you should be aware of. And with that, now we are in a position to move on to a more detailed understanding of some of these aspects. So let us start with stress and strain. Okay, so now every time we talk about stress and strain, we always talk about stress and strain when we are talking about deformation, but then we need to define it at some point. So let us start with the definition. Now to begin with, you must understand that there are actually two different definitions of stresses based on what is the parameter you are using. What is that? Particularly when we are talking about deformation. So stress is nothing but force per unit area. Now here, if you are deforming, then of course this area will change, and if this area changes, therefore you have to determine or you have to ask whether you are talking about instantaneous area or you are talking about original area, and based on that this stress value would change, and it will be called engineering stress or the true stress. But in order to define this, we will need the value of strain, and therefore I would first describe strain over here. Strain, particularly the engineering strain, so I will write engineering strain. Again we talk about change in length per unit length, that is the usual definition given for strain, but that is actually the engineering strain. Why? Because length that we are taking over here is usually the original length at the beginning of the deformation. If you have done some amount of deformation, then we say that what is the total change with respect to that original length that was there at the beginning. However, at each and every instant of time during deformation, the length was also changing, and therefore the strain value at a particular instant would also be different, because you will use a different L value, and therefore we need to be therefore we have these two different definition of strain, engineering strain and the true strain. So this first let us look at our usual, the more common and easy one, which is the engineering strain. So this is change in length by if you are talking about a very small amount of deformation, or if you are not interested in very high precision, then engineering strain is sufficient. So if strain is low, or limited precision is required, then you use this engineering strain. Now, let us say you deform a material to some extent, then you again perform another step and you deform it even further, and then you do such kind of multiple steps. So, in that case you would be interested in finding out what is the total strain that has been imposed on the material, assuming for the time being, let us say that it is unidirectional strain. Of course, strain can also be multi-axial. So, let us say for the time being that we are talking about uniaxial strain. So, what will be the total strain after each of these multiple steps? In that case, we cannot just take this value, because as we saw at each and every instant the strain was changing, and therefore, what we represent at the end is not really the true strain, and therefore, we need a different definition for strain, usually defined or in our particularly in our course we will use this symbol for true strain. So, right now I will put a subscript true. So, this defines instantaneous change in value. So, u is the displacement, x is the point at which this instantaneous displacement has taken place, or if you were to approximate it, this will become limit delta u by delta x, x tending to 0. So, this will be your definition, mathematical definition of true strain. So, this is actually talking about strain at each and every point in time, and therefore, it is also talking about change in the denominator, which earlier we were assuming to be a constant value. So, now whatever strain we get is actually a true representation of the strain, and therefore, you can add it if you have multiple steps. And it can be very easily shown that if you have a unidirectional deformation, then this can be, if L was the starting and LF is the final, then this will become dl by L, which is equal to ln LF by L, and therefore, you can again LF is the final length and LF minus L would be our delta L. So, we can relate it to the engineering strain, and this will come out to one plus E. So, we are using E for the engineering strain and epsilon for the true strain. So, your epsilon or the true strain is actually natural log of 1 plus E. So, do not get scared by all these equations. These are just straightforward things, but when we put this in a formal way, it may look a little intimidating, but these are nothing scary about all these. So, all you need to remember at this point is that there are two kinds of strains, the engineering strain and the true strain, and if you want to find the value of true strain, you can use this equation, which is ln 1 plus E, where E is the engineering strain, and engineering strain we know is very straightforward to find, delta L by L. So, that is the message from this. So, that was for strain. Now, similarly, we will have two different equations for stresses, engineering stress and true stress. Stress, if you remember, is given by force by area. Now, again what we mentioned earlier, that if your area itself is changing, then it means that your stress should also be changing, and therefore, if you want the instantaneous stress, you will have to have instantaneous area, just like if you wanted to have instantaneous strain, you needed to have instantaneous denominator value, and that is why the true strain value was more accurate. If you take F by A naught, where A naught is your original area, even after deformation, if you take this, then this gives you the engineering stress. So, this is your what change do we need to make if we want to make it a true strain, or sorry, the true stress, then we need to change it to F over A instantaneous. So, we will come back to this equation again in the next class. So, just remember that there are two different strains and two different stress. We will will show what will be the equation or relation for sigma true, just like we had the relation for true strain, we can also have a relation for true stress. So, we will come back to this in the next class.